tries to address the hierarchy problem. So of course, most of you know about the hierarchy problem. So I'll give a very quick introduction. So the hierarchy problem arises if you try to write the Higgs mass, the physical Higgs mass. So here I've written in terms of mu h squared, but once you know mu h, you know also the Higgs mass. So if you try to write the physical Higgs mass in terms of the parameters of a UV theory. So let's say at some high scale, so high energy scale is like small length scale. So small length scales are always more fundamental. We always try to describe macroscopic things in terms of microscopic things. So so small length scale. So suppose you have some, so suppose you have this term, this h dagger h term, and the mu, and you have a way to calculate. So one of the assumptions that is going into this is that there is some theory which tells you in terms of the parameters of that theory. So this alpha I UV is some UV theory with its own parameters. So in terms of the parameters of that theory, you know what sorry, this should be mu h. So there are two mu's here. One is the renormalization scale that is just mu, and this is mu h. So this should have been mu h. So let's say mu h is calculable in this theory. So in terms of the UV parameters, you know what mu h is. And then you run down, and these green lines are like threshold corrections. So whenever you see a green line, as you run down from high energies to low energy, there is some new particle that's coupling to the Higgs. And as soon as that happens, you get a new loop correction. So for example, here, maybe there's some particle at the Planck scale, there's something at Guth scale, then there's something at TeV scale. So in the end, when you will predict the Higgs mass, you'll pick up all these contributions and you'll get an expression like this. Now, as you well know, that if these masses are very big, for example, if there's an order Planck square correction, there might be an order Guth, maybe you have some new physics at Guth scale, or maybe you have some new physics at the TeV scale. So these numbers are pretty big. Even if it is at TeV scale, it's pretty big, whereas the left-hand side is just about 10 to the 4 GeV squared. So what this means is that to get this small number from these big numbers, you need to, so this small number can be obtained only in a very small fraction of the UV parameter space. So if you want to write, so only a very small region of the UV parameter space will be consistent with a light Higgs. Now, of course, you might solve the hierarchy problem up to a certain scale, but even then you should, so even if let's say above 10 TeV you solve the hierarchy problem, but even then this 1 TeV squared number is starting to get big. So so that is in short what the hierarchy problem is when you're trying to write the Higgs mass in terms of some UV parameters. And of course, we know that the most of the solutions to the hierarchy problem used some symmetry. So there were these so-called symmetry-based approaches. So in these approaches, you embed the standard model in some other framework, in some more elaborate framework where there's some symmetry which prohibits the Higgs mass. So in other words, if mh becomes 0, or if this mu h becomes 0, that is that enhances the symmetry. So the mh is protected by symmetry, and a corollary of this is, of course, that whatever is breaking the symmetry, because there is no such symmetry in the standard model that can protect the Higgs mass. So whatever is breaking this symmetry, for example, if it's SUSY, it's the soft SUSY masses. If it's if the Higgs is like Goldstone, if it's a shift symmetry, then there is some. So whatever is breaking that symmetry, the Higgs mass should be of that order. Now that would predict that you should see new particles around the Higgs mass, but we haven't seen any such new particles. So this is very briefly the argument why people used to believe that the Higgs mass, the fact that the Higgs mass is around a few hundred GeVs, that should predict other particles close to the LHC, as Kajari also mentioned in her talk, that people expected not just to see the Higgs but other states that have unfortunately not been seen so far. So the LHC now results are telling us that we have seen so far no such states. Of course, this might change. So as Kajari was saying, maybe in the next decade we will see some new particles, but already we are a decade since the discovery of the Higgs boson. So we can at least think about this question: what if the LHC doesn't see any new physics also in the future? So was this argument wrong? What was wrong? So my philosophy is that maybe it was wrong, and of course it would be wrong if you don't see anything new. It would be wrong, but maybe it points, but maybe it's wrong in an interesting way. So what that means is that so one of the assumptions that went into this argument must be wrong, and then you can try to think what was the loophole in the argument. So I found this quote, and so Niels Bohr said that the opposite of a fact is a falsehood, but the opposite of one profound truth may well be another profound truth. So maybe the hierarchy problem argument was wrong, but because it's not easy to find a loophole, I mean, of course, there are various assumptions, and there are well-known ways. Now people know how to maybe get around this, but each of these different ways, there are not so many different ways of getting or finding a loophole. So in some sense, if you want to solve the hierarchy problem today and you don't want to have any new physics at the TeV scale, it's a more constrained thing. It's not like anything goes. It's only maybe there are a few ways of getting around it. And that's why maybe it's interesting theoretically, because there aren't, so in some sense, before the LHC null results, you could write hundreds of models, but now maybe it's much more constrained to write a model that is, in fact, as you will see, it is quite difficult to write a model that can accommodate a light Higgs and no new physics at the LHC. So there are various new approaches. So there are some approaches which says, okay, maybe there are no new physics till the Planck scale, and somehow gravity also doesn't give any new corrections. So one of the approach that I will talk about today is this cosmological selection approach. And one way to introduce it is to say that we were saying, so in the beginning, the first slide I showed, I said, okay, so if you know so if you try to predict the Higgs mass in terms of the UV, then there are then you run into this problem that the UV parameter space must be very you have to fine tune in the UV parameter space to get a light Higgs. But one possibility is, of course, that there is this, so there is no one-to-one relationship between the Higgs mass in the IR and the UV in the UV theory. So what if the fundamental theory has many ground states, so many phases, and this can easily happen, right? You have many scalars in the UV, the scalars get wave. Let's say these scalars couple to H dagger H, and so phi I H dagger H. So in different vacuum states, you will have different Higgs masses. So maybe instead of there being a one-to-one relationship, you have different Higgs masses. And of course, it's well known that this happens in string theory, but you can also easily do it in a field theoretic setup. Just have many scalars and all of them coupled to H dagger H. And this, let's say you have n scalars, they have some complicated potential. And in general, they have two to the n or e to the n vacua if you try to minimize. And in each of these vacua, the Higgs mass may be different. So this is a logical possibility that we must think about. So this is what I would mean by a landscape, that in the IR, there are many, many ground states, many different vacua where in each the Higgs mass is different. Okay, so now, so in the next few slides, I'm going to review. So there have been solutions that have been proposed, as you will see in the last decade, which use this kind of an idea. So let's say there are many vacua. And again, because of this, because of what we saw in the first slide, most of these vacuas will indeed have the Higgs mu squared very high, like m Planck square or m Guth square or whatever. But in some very small number, just by accident, you might have a Higgs mass square that is small. So maybe here I've written 2, but maybe this will be 2 out of billions, where the Higgs mass just accidentally will be small. So if you scan over all possible vacua, and you have many, many of these vacua, so just by chance, some will have a small Higgs mass. And now if you have a mechanism to select these small ones, then you can find an explanation for the lightness of the Higgs. Now, one mechanism that is known, but it was proposed in this paper, is the anthropic selection. So it turns out that if the Higgs wave was too large, then proton or neutron won't be stable. You can see the details because basically the contribution of the up and down mass, the bare masses, the up and down mass, because as you know, the proton is mostly the masses coming from QCD, but if the wave is high, then mu md start contributing, and the neutron proton mass difference changes, and then you can have all kinds of things. But of course, this kind of assumes that you are keeping the Yukawas fixed and changing the wave. But so basically, the anthropic argument selects some range of mu and md, not the electroweak wave, because you can imagine that the Yukawas are also changing in your landscape, and then you can't say much. So this is maybe one flaw of this argument. So you have to find a reason why the U covers don't change so much, and if only the waves change, then you can say, okay, only in some of these regions of this landscape are consistent with there being life. So since we have observed, we know there's a life, that's an observation, and that constraints that tells you. So this is one approach, but there have been recently many approaches where you find a non-anthropic selection mechanism. So you have this landscape, and then you find some non-anthropic mechanism, and typically these things add some scalars, and the dynamics of the scalar is such that only some of these vacua get selected. And the good thing is that unlike anthropic models, they have clear signatures. You can see the scalar, there's weak scale physics and so on. And again, there are not so many. So one of the first papers was this Relaxion paper, where it wasn't like they even needed a landscape. So they had some slowly rolling field which could in time scan all these different vacua, and then once you get close to this 100 GeV scale, it stops. And why? So these are some of the papers, and most of them are from the last decade, as you see, which try to find this kind of an explanation. And so our work is is a continuation of this approach. And so there is some principle that almost all of them are using, and the principle is that now the mu squared, as I said, that earlier approaches, symmetry-based approaches, used to say that mu squared going to 0 is special because you recover some symmetry. But in these models, mu squared equal to 0 is not special because of it recovers some symmetry. Indeed, as you saw, symmetry-based solutions are hard to accommodate. It's hard to accommodate them with LHC null results. Mu squared equal to 0 is special because it separates two phases. So another way of phrasing the hierarchy problem is that the mu squared of the Higgs is very close to the point which separates the two phases, the electroweak symmetry breaking and preserving phases. So maybe something happens near this critical point that so basically what happens is that the Higgs wave plays some dynamical role and is so you will see. So basically there is some light scalar that couples to the Higgs wave, and whether or not the Higgs has a wave plays a decisive role in the dynamics of the scalar. So this is like, if I have to really summarize it very quickly, what these models do. So so now yeah, but then if you have new physics, you always break it by true, that is true. But it's hard to use that because as soon as you have new physics, then you break with the cutoff that conflict. So so large extra dimensions also you expect new physics at the LHC. But here also you will see in some roundabout way new physics will come. But here the goal is that you have a very high cutoff. And then so typically the Higgs mass in any of these kind of vacua is ordered that cutoff, m Planck square or m Gutt square. In our case, it will be something like 10 to the 10 GeV. And so you don't, and everything is in 4 dimensions here. Okay. So so already there is one physical quantity which behaves in a very special way near mu squared equal to 0 already in the standard model, and that is the vacuum energy of the Higgs. By the vacuum energy of the Higgs, I just mean the value of VH at the minima. So if I have mu squared equal to 0, I know that the Higgs gets stabilized at the origin. Now, as I keep lowering mu squared, so this is a lower value of mu squared, the orange, and then I keep lowering it, I go to the green. What I see is that the vacuum energy is decreasing. So vacuum energy is decreased. So now if I plot this, I'll get, if I plot this, I get something like this. So if mu squared is positive, the Higgs vacuum energy doesn't change at all. It's constant, it's at 0 classically. And then when mu squared starts decreasing, if you go back, the Higgs vacuum becomes deeper and deeper. So that tells me that the Higgs vacuum energy does something special around mu squared. So once it gets a wave, the Higgs vacuum energy behaves in a very different way. It keeps going down monotonically. So this suggests a selection mechanism. And so how can we use the fact? What does the vacuum energy couple to? Of course, gravity. So what can happen is during inflation, and this was actually in a different kind of a model. It was suggested first in this paper and also used in these other papers. What can happen is that if the Higgs vacuum, so during inflation, you have different causally disconnected patches. And if and very naturally, these patches can sample different vacua. So because there are quantum fluctuations, you don't have to do anything extra. If you have inflation, then different patches, the scalar field values are different. In general, they can be in different vacua. And then you can see that the effective parameters in each of these patches are different. And in one, if the vacuum energy is much bigger than the other because of, as you know, exponential expansion, in a very short time, this kind of patch will dominate everything. So this kind of mechanism was used here, but in a very different setup that maybe I'll briefly mention. So we borrow this idea from these papers, but we try to construct a very simple example of a model. So in other words, large Higgs waves are disfavored over small Higgs waves. So small negative Higgs masses would be, so if you just had standard model, let's say, and there was some mechanism or some way of having different mu squared in each patch, then automatically you see that the very big large negative mu squareds won't expand much. Only the positive mu squareds or the small negative mu squareds will, because very big, very negative mu squareds will mean large wave and very deep Higgs minima, so they will have smaller vacuum. Of course, I'm assuming all kinds of things. Vacuum energy won't just come from Higgs, it would come from other places also. But very naively, you can make a model like this. Sorry. So you see here, so as I said, I had all these different bubbles which are like these different patches. So I can already, just at the level of standard model, if maybe I can make a model where you can exclude very large negative mu squared values just because the vacuum energy is so low in that. But the issue is that any positive value of mu squared will still get selected, because then you are, in fact, any positive mu squared, the vacuum energy, there's a plateau. The vacuum energy is the same and at its maximal value for any positive mu squared. So these will get selected. Okay. So, so what we did, motivated by this, so you can just do a simple model where VH, which is the Higgs potential, as I said, large wave implies low vacuum energy, so large waves would be, or large negative mu squared values will be excluded. But then we add a scalar phi such that this term, which is sometimes in this literature called the trigger term, the scalar phi potential will depend on the Higgs wave in such a way that if the Higgs gets wave, this term will give a negative contribution. So let me show you a simple example. For example, if you have a scalar which has, if the Higgs wave is 0, let's say it has a Mexican hat potential. And then as soon as the Higgs gets a wave, you go from this to this and you raise the vacuum energy of this scalar. Okay, I should be done well. So you raise the vacuum energy if the Higgs gets a wave. Okay. Now, of course, you don't raise it beyond a certain value. You just sit here after. So after some threshold, after this kappa h squared is equal to m squared, you don't raise. Now, in patches where the Higgs wave is much bigger, you don't raise it any further, but then the Higgs part of the potential starts getting more and more negative. So in the overall, your vacuum energy will peak at a small Higgs wave, not for Higgs wave 0, but at a small but finite Higgs wave. The problem with this model, however, would be that if you write this term, then you should also write a term. So because we want a very high scale of new physics, you can just close the Higgs loop and you could have written this term already. And this is kind of quite a common problem in these kind of models. Although I should say that if you look at these models, they're completely different. This model is completely different from the other models, but there are some universal features, because all of these models have some field phi and then they have to couple it to the Higgs. So if you couple it like this, so whatever this H dagger H wave will do, this term will already do that, right? Unless lambda is less than 4 pi v. So unless you have some new physics that cuts off this loop, so you're back to the same problem. Unless lambda is less than 4 pi v, you could already have had a term that did this for you, and so this kind of a term is problematic because of that reason. And this is, as I said, quite a general issue. In fact, this was argued in this paper that it's quite a generic issue, that whatever can be triggered by H dagger H can also be triggered by closing the loop. So this is, and because of this, you have to do something more. So either you have to cut off this loop, have some new dynamics that at the TV scale below this 4 pi v. Or the other option is to go to a 2 Higgs doublet model, which is the more neater option. So instead of having 1 Higgs, you have 2 Higgs doublets. And then now the term looks something like this. Now you can't close the loop. So now this term looks like this, and you can show that you don't have a big enough. So at the loop level, you can't generate a term that is phi squared times something order electroweak wave. So that is guaranteed by having this, and then there's some symmetry Z2. You can show that even at 2 loop level, you don't generate a dangerous contribution and so on. And so basically we have some kind of light scalar phi. So now let me, because this was just kind of motivation, but now the actual model I can go through very quickly because of all this big background that I've given. So this phi has something like a pseudo-Nambu-Goldstone boson potential. So it is a much lighter. So the mass of phi is much lighter than F, and you can generate this in many different ways. This is a generic PNGB potential. And then you have a 2HDM, which is again a very generic kind of 2HDM with this kind of discrete symmetry. And you have a term which breaks both the shift symmetry of the phi and Z2. And we have checked that everything is kind of so for example, this breaking should not be too big. This should not induce a term bigger than this mu squared and all that. We analyze all these constraints. And then what we want to do is now we want to maximize the vacuum energy of this potential. And hopefully it will be maximized at a small Higgs wave, which is much smaller than the cutoff. Now, so let's say now I go to the cosmological picture where we have many kind of vacua. In each vacua, the parameters of my low energy theory are different. In particular, the parameters of this 2HDM, these lambdas and mu's are different. So for example, this alpha HI tells me the parameters of the 2HDM sector, and they're different in different vacua. Then there's some inflaton contribution because I'm doing inflation, so I must have this term. There's some C3 contribution. Now, now you can show quite generically that it's done in papers much before related to inflation and internal inflation, that during inflation, it's quite generic that if you have many vacua, that you go to the highest vacuum energy state, as we were saying. And this has been done quite rigorously in many papers, and it's also reviewed in our work. So it's quite generic. You will go to the highest energy state, and we'll assume that highest energy state will have each of these terms maximized. So you could have asked me, why are you just looking at the Higgs contribution? You have a CC, you have other things that can contribute to the vacuum energy. But it turns out all of these must be independently maximized, including the Higgs contribution. So with that, so that tells us that it makes sense to maximize this individually. And then we need another assumption, because you see, during inflation, it's not like every field is at its minima. The fields can, there's some quantum spreading. So the fields can deviate from their minima. So, so you have this so-called probability distribution. You have these probability distributions. They're not exactly like probabilities, but which you have to solve this Fokker-Planck equation to get them and so on. And you can show that under certain conditions, the fields do peak at their minima if the Hubble scale, if you satisfy these constraints. Basically, the Hubble scale has to be much less than the weak scale and so on. Under these conditions, you can show that even during inflation, all the fields will be at their minima. So otherwise, the whole exercise doesn't make sense. Now, if that happens, because the Hubble scale is less than V and our cutoff will be order the vacuum energy during inflation, that gives a bound on our cutoff, which is 10 to the 10 GeV. So this unfortunately tells us, because the Hubble scale cannot be bigger than V, that our theory has a cutoff of 10 to the 10 GeV. Now, so now most of the main part of the work in this paper was to look at this 2HDM potential, phi plus 2HDM, minimize it, find the vacuum energy, and then vary the parameters to find where the vacuum energy peaks. So we can do this in two steps. We can first what we did is we varied mu1 squared and mu2 squared. Varying mu1 and mu2 squared is kind of like varying V1 and V2, like the minimization conditions. You can trade mu1 and mu2 for V1 and V2, the wave of the two Higgs doublets. And that is like varying V and tan beta, basically. So we vary V and tan beta to maximize this whole potential. And then in the next step, we will vary the quartics and try to maximize the potential with respect to that variation. So first, just the variation of mu1 and mu2 square. As I said, the very simple picture that I said at the beginning actually holds under there are various subtleties that I will discuss a bit. So if the Higgs wave is 0, as you know, the Higgs potential is like this, but the phi potential to start with was like this. Now, as I increase the Higgs wave, at some point the phi potential flips from this to this form, but the Higgs potential becomes a bit more, it dips a bit. And then once I keep increasing the Higgs wave, the Higgs mu squared in vacuum where the Higgs mu squared is very large, the phi is settled here, but the Higgs potential becomes deeper and deeper. So now if you look at the vacuum energy, it is maximized in this middle panel. So the vacuum energy is maximized for a Higgs wave which is 100 GeV, and indeed this is much smaller than the cutoff, which is like 10 to the 10 GeV for us. And so this is once you vary mu1 and mu1 squared and mu2 squared. Now what is interesting is, and this is what we spent a lot of time doing actually, is that what was that? Yeah.
As
so
the
point is, if I try to minimize this potential, and right now I'm just varying mu1 squared and mu2 squared. So I say that there are various, sorry. So I'm saying there are various vacuum, and let's imagine for the moment that the only thing different between the different patches is that the value of mu1 squared and mu2 squared is different. And now I try to maximize this term, this Higgs contribution to the vacuum energy. And then it's an exercise, like basically I'm minimizing things.
So this 100 GeV emerges.
No, 100 is order 100.
Yeah, I understand. I mean, it is 10 to the 2, 3, whatever it is.
Yeah, it's much smaller than the cutoff. That's the whole.
It's and your cutoff, the 10 to the 10 GeV.
Yeah.
And that you got from.
So I will show you. Let me show you the expression. So it emerges because as you see, once the Higgs wave, if the Higgs wave is 0, this is at the potentials of both the things are fixed completely. Okay, this is a fixed Mexican hat potential, and your total vacuum energy is this negative value. Once I start increasing the Higgs wave at a specific value, that of course doesn't need to be 100 GeV, but there's no reason for this value to be of the order of cutoff. It's basically this value comes from here. Basically, I want to, basically you see here that this PNGB has a negative mass squared, right? And this Higgs wave is making that positive. So if I make the Higgs wave large enough, the mass squared here will flip the sign. Okay. And the value where that flips has nothing to do with the cutoff. It's because this mu wave, this is a technically natural thing that can be much smaller than the cutoff.
No, I'm just wondering, I mean, without any other reference point, you are getting some number which is of the ballpark of weak scale. I mean,
no, that's true. So that maybe I should have said, no, that's not. So basically what we'll get is it's maximized at this thing. So at this value mu phi f, which can be weak scale, which can be electron volts, anything. But then you have to choose your mu phi and f to give you the observed weak scale. So this could have been anything. This could have been, but the whole point is this can be much smaller than the cutoff. Now, what it actually is depends on the observation that the weak scale is 100 GeV. So mu phi f must be equal to 100 GeV. But it could have been 1 electron volt also, basically anything. Like these are free parameters in my theory. So I will fix them to get 100 GeV.
The corrections to mu phi f due to loop corrections, that is under control, or can lift it to the cutoff?
Yes, because this is like the parameter that breaks the shift symmetry. So it's completely correction is multiplicatively corrections to mu phi are of order mu phi or something. Yeah.
Mu phi itself is not technically natural, I thought.
No, it is. Mu phi is the, sorry, I'm going in the other direction. Sorry. Mu phi is the, very quickly I can, but we can discuss later. Mu phi is part of the phi potential. So it's, if it's a PNGB, then it's, sure. Okay, so so mu phi I can discuss, but it's, you can show that that potential will get, mu phi will get corrections that are multiplicative. Okay, so this picture which holds, I mean, this is a very simplistic picture, but there are various subtleties. This will hold only, it turns out, if the quartic satisfies certain conditions. So for example, there are much more complicated, once you do the minimization, you could have had that both the phi and the Higgs gets a wave and things like that. But that, to prohibit all those kind of things happening that can kind of spoil this picture, you need various conditions on the quartics. And this might have been, I mean, we do this in 2H DIMMs all the time, that the quartics have certain conditions. And of course, like for example, if there are other phenomenological things, for example, if this is not true, the photon can get mass and so on. But the nice feature of our model is that all these conditions we found on the quartics, once we were varying mu h squared, the two mu squares, they can automatically get selected in the second step. So when you vary the quartics, it turns out that if you respect these conditions, only then the vacuum energy is maximized. So first we were maximizing vacuum energy with respect to the variation of the mu squared, but if you do it with respect to the variation of the quartics, it turns out that you will automatically select this region. So we don't have to impose any of these conditions, they naturally are okay. I'm just too much stream. Okay, so so that is basically the thing, and then in the end what happens is that in the beginning you can have patches with all kinds of electroweak wave, but the ones which are this maximal energy ones get expand and occupy most of the volume. So that's the essence of our mechanism. So very quickly, the one thing I wanted to say is that to connect to some experimental facts is that this condition, so when, as I said, I was maximizing with respect to V1 and V2, so that gave me some condition where it is maximized in with respect to the V and also tan beta, because V1 and V2, there are two parameters. So our model gives a prediction for what tan beta is, and that it can be experimentally verified. So this condition that the vacuum energy is maximized at this place can be turned into this equation which connects alpha, beta. All of these are observable things, as you know, people who are familiar with 2HDM phenomenology. Some like beta can be measured by charged Higgs and pseudoscalar decays. Alpha is related to the CP even Higgs couplings and so on. So all these things can be measured. Why can't I go? Sorry. It seems stuck. Sorry, I have 2 more slides left. Yeah. Okay. So this is a slide where we show we can predict basically the value of cos alpha beta for a given value of the heavy CP even Higgs and tan beta, and this is of course can be measured in if you may measure couplings of the CP even of the standard model like Higgs coupling deviations, you can measure this thing and we can predict it. So in terms of 2 other measurable parameters, we predict a third, so which is a nice feature of this. And of course the phi itself has its own phenomenology, and it can be dark matter in some region, and there can be bounds from equivalence principle violation, and those have been shown here. So this is very quickly to say that there are very clear phenomenological signatures, and I will just skip this part. So there are previous works that do this, but the main difference is that they try to have a mechanism for scanning the Higgs mass, and for that then they require very complicated kind of potentials. The other papers I was showing you. So basically they require something like the relaxion potential, where you have a periodic term, or and these are very contrived. So this can be motivated if you have something like a clockwork mechanism, and the clockwork is, as you know, many scalars with a very specific potential. So in some sense it's very contrived to get these kind of potentials, and so all these models have this potential, these 3 models. And because we are doing something more minimal, we don't want a mechanism that scans the mu squared in different vacua, we just use the phi for selection, we don't encounter this problem. And there are many nice features. For example, in those models have some crazy things always in those models. For example, the field value of phi is trans-Planckian or above the F, or the number of E-folds is very, very large. But in our model is much simpler and also doesn't have these issues. So I'll let you read the conclusions. Thank you.
I think you want to wait till the end of the session, because the organizers told me to be strict with the time. So I'm sorry,
No,
I
it's
cannot take
okay.
any question, and I'm sorry, you can talk to him later. So the next talk will be by Ranjan Laha, primordial power spectrum in light of JWST observations of high redshift galaxies. Yes. Yes.
If you can actually please postpone your questions to the tea time, so that we stick to the time. Thanks.
Okay. So welcome everybody. First of all, I would like to thank the organizers for inviting me to this exciting conference. I'd like to thank all of you for being here. So I'm talking about something that I'm quite excited about, is how do you use the recent JWST observations. JWST stands for James Webb Space Telescope. You must have heard it got launched in the on Christmas Day of 2021 to study fundamental physics. So in this work, I'll be talking about primordial power spectrum and tell you what that is. So this work has been done entirely by Priyank Parashari, who was a postdoc in IISc with me. Currently, he's a postdoc in University of Southern California. So all the good things that have come out of it is because of him. Okay, so let's do. I can change the slides. Okay, so I'll first introduce cosmology and James Webb Space Telescope, since this is a very wide audience, and then I'll be talking about two of our main works, how you can probe either the red tilt and the blue tilt. I'll explain what those are using JWST observations. In fact, how you can get the best limit in the world using JWST observations of the red tilt. Okay, cosmology and JWST. Okay, so we know cosmology extremely well. All right, so this is a cartoon that we have taken from Robertson et al., which shows the timeline of the universe. So obviously, we have all heard of CMB. This happened at this redshift, the redshift 1100, when the age of the universe was 370,000 years. After that, there was this region of dark ages, and you see here we have lots of question marks. We do not know that. We do not know when did the first stars form. We do not know the answer. When did the first galaxies form? We do not know the answer. How did reionization start? We do not know the answer. All right, and then there is this region beyond, I would say, redshift when redshift is less than 10, when we have some observables. One of the things which Abhijit talked about is using the Lyman alpha forest to study primordial black holes. And then finally, we have the low redshift universe, where we have excellent observations, right? So this is a plot of the CMB power spectrum. All of you have seen this, and this is the cosmic pie chart, right? Dark matter makes up 27%, ordinary matter 5%, and dark energy 68%. So it turns out these numbers we know extremely well, right? To less than 1% accuracy. So this is a screenshot I took from the PDG of the PDG recommended values of the 6-parameter lambda CDM cosmology. Or what are the values of parameters? The baryon density, as you see, these numbers are known extremely well, the cold dark matter density, and at least for the purpose of this talk, the scalar spectral index from this thing. So these numbers are known to less than 1% accuracy. That's how well we know the early universe. The question is, how do we probe lambda CDM more precisely, or how do we probe in regions which we have never seen before? So this was already hinted at in my previous slide. If you look at this plot, CMB we know extremely well. Low redshift, we know it quite well, but this dark region is something we do not know at all. All right. So the question is, can I do new physics by studying this thing? All right. In fact, before the launch of JWST, we have had almost no clue of what is happening. Even now, we don't really have it, but JWST is really pushing the frontier. All right. So the idea here will be to use the earliest galaxies that JWST has observed. I'll give some details on that, and how you can study at least one fundamental question about particle physics, astrophysics, cosmology, whatever you want to say. Okay, so the earliest galaxies observed. So this is two cartoons, one from NASA and another from ESA, the European Space Agency. So this is a plot of how stars emit. Stars emit almost like a black body. Younger stars are hotter, thus they emit mostly in the UV length, right? So this is the Kirchhoff's law that you have studied in school or undergrad. And then the UV light is emitted, and the UV light gets stretched because of the expansion of space. So because of this again you must have studied. So the farther, if you want to probe far away galaxies, we need to probe redder and redder wavelengths. So that is what this plot is showing. All right. So this is what this plot is showing is some example, 3 examples of various galaxies at redshift 10, redshift 11, and redshift 12. Those are the corresponding ages of the universe, and those are the distances. Because redshift 12 is farther away than redshift 10, obviously the spectrum of this galaxy has shifted to the redder range. All right. So this is actually more precisely the photometry thing, and this is the spectral thing. So you can use the spectra to really know where these galaxies are, right? And then the question is, how do these galaxies form? Right. So that's the thing that we're doing. So basically, as you can see, in order to observe earlier galaxy formation, the earliest galaxy formation, we need IR telescopes, optical or IR telescopes. So do we have them? In some sense, yes. Even before JWST, we had them. So this is the electromagnetic spectrum. All of you have learned. So Hubble is mostly in the optical. There is something called the Spitzer, which is actually in the infrared, but it's very small. I'll tell you what it is. And then this is the big thing in the game, James Webb Space Telescope. So how do I understand them? Well, how do you understand its capabilities? You just look at their mirror size. This is just optics, right? So Spitzer mirror is 0.85 meters. This is the mirror that is used for observation. Hubble mirror is 2.4 meters. Webb is 6.6 meters. It's absolutely huge compared to that, and thus they can also go deeper. So this is in the L2 point. This has 4 instruments: NIRSPEC, near infrared spectrograph; NIRCam, near infrared camera; MIDI, mid infrared instrument; and NIRIS, near infrared imager and slitless spectrograph. Right? So all of them are in the infrared range. And here you can see the example of the same part of the sky observed by Hubble and Webb and Spitzer and JWST or Webb. So I'll use Webb and JWST interchangeably. All right. So you can see this is like a day-night comparison. This JWST has opened up things, and all of you must have seen these beautiful pictures. The question is, what can we do with it? All right. So we can do lots of things, and astronomers are having a lot of fun with this instrument. This is like opening up a completely new way to study, do astronomy. So this is one of the latest compilations by this astronomy group, the Shen et al. What is plotted is, I'll explain these plots. So these are at various redshifts, redshift 9, 10, 11, 12, and 16. What is plotted on the x-axis is the UV magnitude at the point when at the galaxy point, right? So this is brighter, this is dimmer. So this is astronomy. So you have to be a bit careful with these things. And what is plotted on the y-axis in all of these plots are the differential flux density. Right? You can also think of it so per unit volume, per unit magnitude. All right. So these are brighter galaxies. So all of these things, this region is brighter galaxies, and these are dimmer galaxies, intrinsically dimmer galaxies. So we know that brighter galaxies are in bigger halos. So obviously they are less in number. So that's why you see the number density of here is lower, right? Whereas dimmer galaxies are more in number. They're in lighter dark matter halos, so they're more in number. All right. That's one way to understand. The other way to understand, so there are these various lines, 100%, 30%, all of these things. These tell you how do you this tell you some lambda CDM expectations, and this is the thing that we will play with. All right, so all of these lines we can talk about in detail. It depends on what is the dust attenuation. That's an important thing. People are still studying. We don't know this. In fact, at redshift, these two are like really new. We really have no idea how the universe looked like at this redshift. And here at redshift 10, we had 1 or 2 galaxies. All right, redshift 9, okay, we had a few. All right, most of these galaxies have been confirmed spectroscopically. Once you get spectra, you know the redshift extremely well. All right, and some of these galaxies are also known photometrically. Photometrically is just taking a photo and trying to figure out the redshift from something called the Lyman break or the Balmer break. That's, in fact, that is actually working quite well. There has not been catastrophic failures. 2 or 3 examples are there, but besides that, we have many different galaxies which are discovered by JWST. There has been maybe less than 10 catastrophic failures. So even photometric redshift is important, but yes, JWST has spectra, which is the gold standard. All right. So these are some references, some old references. So as I said, all the astronomers, if you open the archive, they just have gone crazy of doing these things. As I said, most of the galaxy candidates which were identified photometrically have been confirmed by spectroscopic observations. All right. So the question is, how do these galaxies form so early? How early is this? This is just 600 million years after the Big Bang. This is really, really early. We did not expect galaxy formation to happen. I'll show you in one of the later slides to happen so early, right? So the question that Priyank and me were interested in, can we test the lambda CDM cosmology using these JWST datasets? Now, sir, we just think about it. It's a complicated question. Why? Because galaxy formation is complicated physics. This is n-body physics, and trying to do large-scale simulations. There are specialized groups for this. And then again, there's baryons. This makes the game even more complicated. And these were the first cosmological observations at these redshifts. And there were a few numerical simulations before this. They did not agree. So we didn't have much to go with. But again, we were still interested. Can we use semi-analytical arguments to probe this? Well, it turned out yes. So there have been a long list of work, starting from this work by Presch and Schechter, where they showed that even if you cannot understand galaxy formation from first principles, using semi-analytical arguments, you can actually get a statistical measure of the galaxy formation. And that is good enough. I'll show how that is good enough. All right. So you can calculate what is something called the halo mass function, which is the number of dark matter halos per unit mass per unit volume that you can calculate. Using this Press-Schechter formalism, this depends on various different things. What is the mean density of the universe at the redshift that you're looking at? What is the dark matter halo mass that you're talking about, capital M? And what is the mass variance of the, what is the dark matter, what is the variance in the dark matter density in that patch of the sky, right? Which basically is signified by the thing R, right? The radius R. So these are there in standard cosmology textbooks. However, as I said, this is semi-analytical. You do need some numerical simulation which comes in from this fitting function, right? The Press-Schechter or the Scherz-Torment fitting function, or there are some others also. All right, so you can do this, and the region where primordial power spectrum comes in, primordial power spectrum is something that is dictated by inflation, is from here. When you calculate this mass variance, you have to do this formula. You can forget the details for now, but there's something called the power spectrum, which is measurable, and that depends on the primordial power spectrum, which is proportional to k to the power ns, right? K is the wave number, which identifies the size of the patch you're looking at, inverse of the size, and t square is something called the transfer function that just tells you how the horizon, how the sub-horizon modes evolve. Also be super horizon, but how the modes evolve. Here we will just assume lambda CDM cosmology. So we will just play around with this primordial power spectrum. And this is a plot which Priyank made. On the x-axis is the mass of the halos in these units. This H inverse, H is 0.67, solar mass, and dm, number of halos per unit mass per unit volume, right? So this is for redshift 0, so this is for redshift 10, this is for redshift 0. So as you can see, as you have heard, lambda CDM in lambda CDM cosmologies, heavier halos form later, so you can easily see this plot, right? So 10 power 13 is not there at redshift 10, but is there at redshift 0, right? So this tells you this thing, and the point is JWST is actually probing these regions at very, very high redshift. Actually these regions, this thing, this right near the tail where this halo mass function is falling. Can we use this to do cosmology? That was the point, to at least probe the primordial power spectrum. So the primordial power spectrum has been probed by various observables, right? So this is the latest compilation that we came across. So what is plotted on the x-axis is the inverse of the length scale that you are probing, which corresponds to some halo mass, right? And this is the linear power spectrum, all right? This line that you see, this line, just this line, is what is predicted from CMB observables, right? You take the CMB observables and then you just extrapolate to high Ks, high values of K. That's what this line is, all right? And all of these constraints come from various observations. Some from CMB, this is the Planck, this is from some galaxy survey, DES PR1, UV luminosity function from the Hubble Space Telescope, Lyman alpha, SDSS, and things like that. And in this work by Gilman et al., they use strong lensing observables to probe the power spectrum in these length scales from approximately 1 to 70. And they say this band is allowed, this gray band is allowed at 68% confidence level, right? The question is that we started with, me and Priyank and me, can we do better? Can we beat them? All right, so let's first parameterize the primordial power spectrum. So this is easy. There are lots of models. Inflation can do weird things, but we just wanted to be model independent. What we did is, so this again the K, the primordial power spectrum. This is the lambda CDM prediction. We have either a blue tilt where there is more power at large scales, or there is a red tilt where there is less power in the large scales, right? So this is a standard thing. And then there's a tilt scale where this thing changes like this, right? So this corresponds to, as I said, the power spectrum enters in the halo mass function, as I showed earlier, corresponds to the halo, how the halo mass function changes. The mass of the dark matter halos in the x-axis, d and dm in the y-axis. This is in lambda CDM. If you have blue tilt, there are more power, so there are more galaxies. You see there are more galaxies, this one blue line. If you have red tilt, there's less power, there's less galaxies, and this is the less galaxies, right? Now what? All right, so that's well and good, but if you think about it carefully, it still doesn't solve the problem. JWST does not observe dark matter halos. Yes. This one is just some numerical thing. Anyway, this is so small mass, we have not measured, so it's not. Yeah, this is calculated from the HMF code, which is the state of the art. Most of it has been done till somewhere, say 10 power 8. So here doesn't really matter too much what is happening. There's probably some numerical thing, and we don't know how to, I mean, the HMF code does not know how to do this. Okay, thanks. Okay, so JWST does not measure the dark matter halo mass. What it measures is the stellar light output. Now we have to convert it to the dark matter halo mass. This is complicated. This is galaxy formation physics. This is really complicated. So what you can do is you can do the most minimal thing possible, which will still be all right. is, let's assume there's a dark matter halo of mass m, and we have to calculate what is the stellar mass. Well, if it's at a redshift z, the cosmic baryon fraction, the amount of baryons that's available in that redshift is omega b by omega m, which is this number. And then you can say the stellar mass will be proportional to the dark matter halo mass times this cosmic baryon fraction times this epsilon. So what does it say? So that says that this dark matter halo takes whatever baryons it is available in that redshift, and that converts a fraction epsilon into stars, and that is the star formation efficiency. This is basically what galaxy formation people are trying to study. All right, and then you can, now using this, you can address various things. You can measure, you can calculate the cumulative co-moving number density, which is this, the d and dm, with us when the halo mass or equivalently the stellar mass is greater than some number. That's what astronomers like to plot, or the cumulative co-moving mass density, which is basically this m d and dm integral. Right. So and as I said, this is from the dark matter halo. You can just convert it for the stellar masses using these relations, and this will work out fine. This was actually first pointed out by Boyle and Kolchin that you can use these things, and in fact, this was based on older paper by Peter Beruzzi and Joseph. Okay, so what can we do? So this is the one of the parts. So using the first results of JWST Cosmic Evolution Early Release Science Sears program, Labbe et al. Identified 6 galaxy candidates. Most of them were initially they were photometrically, but almost all of them were confirmed spectroscopically with a stellar mass greater than 10^10 solar mass at this redshift bin. Right. So this is the plot: redshift on the x-axis, stellar mass on the y-axis, and these are some of the data points. This is astonishing. Why? Milky Way is this. Milky Way stellar mass is 6 times 10^10 solar mass with error bar of ±1. These galaxies, which are at redshift 10, say roughly 7 or 8 or 7, 8, 9, these are as heavy as the Milky Way. This is something we did not expect at all. In fact, Labbe et al. Already plotted this. What they did is plotted the stellar mass and the cumulative stellar mass density. So this were the expectations before JWST launched, these lines. This is the mass density. This is absolutely crazy. Yeah, so that is this part, right? That is this part that you have to take into account. What is the stellar mass density? Sorry, what is the star formation rate? We did not know that. Maybe this is what it's saying. So let's forget exotic physics. Maybe this is saying star formation is really efficient at high redshifts. Did we expect this? The answer is no. Yeah, thanks. We did not expect this. So this is actually telling you something about star formation physics. If you ask some astronomer, they'll be excited. They're super excited about this result. So this is just using the star formation physics that we know from redshift 8 and 9 and trying to extrapolate. Yeah. How do you conclude
about the efficiency?
Yeah, so that's something to know. We do not know this thing. As I said, this epsilon, something we do not know. So that's something to learn. So what you can do is what this thing has done. So HST had data, HST and Spitzer had data at redshift 8 and 9, right? And then you can, that was assuming some star thing. They also had some halo mass, and then you can plot this. And this is what Labbe et al. Is getting. Absolutely crazy. Like we do not know of star formation efficiency being so efficient at these high redshift. We just did not expect this. This is something JWST is saying, teaching us for sure, right? So this is basically what I'm saying. How did such Great. Yes. So JWST is also doing that. And if you really want, this is not there in my talk, you can use, so there's something called the black hole mass and the stellar mass relationship to do that. And that's something Priyank and we discussed a lot, but this was okay. We had to stop our project at some point. We stopped it. Yeah, but this is also, JWST has discovered a huge number of agents at high redshifts. Why? Don't know the answer. Nobody knows the answer. This is happening this last 1-2 years. It's really new. And this is why we started. What can we do? Well, so something that Priyank pointed out is if you have blue tilted primordial power spectrum, as I showed earlier, you can have more massive halos, right? So this is these plots. These plots are very similar. So let me just explain this plot. These are redshift 9. Again, stellar mass on the x-axis, cumulative stellar mass density on the y-axis. If you take lambda CDM, and if you take the star formation efficiency of 20%, which is roughly Milky Way, in fact, Milky Way is slightly lower than that, you get this line. This line. This is the Labbe et al. It's hardly crossing through the Labbe et al. Line. But if you take a blue tilted power spectrum, that means there's slightly more power. So you produce heavier galaxies. Again, using the same epsilon, you get this line. So you see now this nicely goes to the line. I mean, you can also take like 100% star formation efficiency. So this has been proposed after the JWST discovery by Deckel et al. And these are 2 lines, again for lambda CDM and again for blue tilt. This is the same plot at redshift 7.5. So this plot shows that having a blue tilt can plausibly explain these results, right? If you really want to be staying. This is the paper, this is archive number and the journal thing. So this is again in the KP, remember KP was the tilt and MS was the slope. This is the region which explains it. Turns out, but it's not so fast. There have been, as I said, I showed the Gilman et al. Plot, there have been other constraints. And this is what we show in this plot. This is the K, this is the P of K. This line is the lambda CDM. This band is coming from Gilman et al. This is coming from lensing. These are from Lyman alpha, there's from HST. And this blue line that you see is barely the line which can explain Labe et al. And this is clearly in tension. And we showed that okay, blue tilt is probably not the best idea to go forward, like even this. So we did all of this analytically, semi-analytically. Immediately after our paper, Hirano and Yoshida, so they are some numerical simulation people. So they ran numerical simulations with exact same blue tilt power spectrum that we had. And this is what they plotted, exactly the same thing, M star, rho star. This is lambda CDM with some epsilon. If you have a soft tilt or a hard tilt, soft tilt means slight blue tilt, hard tilt means very much blue tilt. As you can see, you can clearly explain this. So exactly the same thing they think. And then following up, not following, they're also doing the same thing. There's a paper by Sapti, Julian Munoz, and Markham and Kasky, where they also showed, okay, if you have this blue tilt, the thing that we showed in this plot, that there will be problems with lensing and HST data. They just talked about the HST data, but there will be problems with lensing also. And we have one long paragraph of what is going on here. At the point of our paper, nobody simply knew what was happening. It was just something weird. Okay, so now the last part. Can we do even something better? Yes, done. So I was talking about the Sears survey. So there's another survey called the JADES survey, JWST Advanced Deep Extragalactic Survey. This was different in the sense that this was just doing spectroscopy at the beginning, right? Spectroscopy is extremely expensive because you have to find the line at the exact redshift. So it's extremely expensive, but they did it. And the first results were from Curtis Lake et al. And Robertson et al., where they found 4 galaxies spectroscopically, right? So these were named GSZ10 at redshift 10, redshift 11, redshift 12, and redshift 30. And you can see the error bars. These are known really precisely. And using this, Keller et al., what they did is they tried to study that is this expected from numerical simulations. And they saw that at least some numerical simulations, Eagle, Illustris, TNG, Simba, with some epsilon is sort of explaining these things. Note that there is a tension between these results and Labe et al. Results. Nobody knows the answer. The part of sky that Labe et al. Looked at was different from JADES. So maybe that part was weird. We don't know the answer. Even till today, we do not know the answer. What is happening there? But still, anyways, so they had these things and they said that, so Keller et al. Did something very simple. They said that, okay, I looked at a patch of the sky. I found 4 galaxies. So that means the number density of the galaxies must be 4 divided by the volume. That's the lower limit. It's a strong lower limit. And that's what they have at various different redshifts. This. All right. And at redshift 10, there were some older data from Spitzer, right? But redshift 11, 12, 13, there was nothing. This was the first time we were seeing it, all right? So this is the region where you can't have any galaxy because you need too much baryons. And this is the star formation efficiency of 10%. So you can see this is much less than 10%. It's like something 3 or 4%. I'll show you in the next plot. So what we did, now it's sort of becomes super trivial. If you think about it, there are these galaxies, there is this strong lower limits. You can't have too much red tilt. Then you will not produce these galaxies, right? So let me rephrase this. So let's look at this plot. They are the same plots. Stellar mass on the x-axis, number density of galaxies with a mass greater than m star in the y-axis. So these are the predictions of from assuming in lambda CDM cosmology, assuming star formation efficiency of 3% and 4%. Suppose I make the power spectrum red tilted, then the line will go like this, say for example, like this. If I just make it crazy, that is not allowed. We have seen galaxies at redshift 13 now, so you cannot do it, right? So using this, we realize we can actually put a constraint on the red tilt of the power spectrum, a region which is probably something new. And this is the result. Again, this is the Gilman et al. Plot. This is a busy plot. Let me explain this step by step. Again, K on the x-axis, power spectrum y-axis. This line is the lambda CDM prediction, well, not prediction, the extrapolation from the Planck thing. This is the Gilman et al. Band. So Gilman said it cannot be more than this or this. They had the band. What we said, remember, we said you cannot have too much red tilt. So we have a lower limit on the red tilt. So these lines depend on what is the pivot scale, how I change the thing. These are lower limits. So anything above is allowed. Anything above is allowed in these lines, right? So let me replot this. pre-angrily plot this in K and delta Pk, but delta Pk is P lambda CDM minus the red tilt by lambda CDM to 100%. This is the line from Gilman et al. This is the percentage deviation. 20-30% deviation from lambda CDM is allowed. We said no, that's too strong. You should probably have not 20-30%, maybe 10 to 15% deviation. And as far as we know, in this length scale from 2 h megaparsec inverse to 7 h megaparsec inverse, this is the most stringent constraint on the red tilt of the primordial power spectrum as of now. Right? This depends on the star formation efficiency, but we have taken the star formation. We have taken a large star formation efficiency, which gives us a conservative limit. You can, if you can take this even smaller, can make this 3%, not 4%. Your limits will be stronger, and 3% is allowed with the Spitzer data. It's not ruled out. You can make it even stronger constraint on this. All right. So these are my conclusions. I hope I'm on time. So I hope I've convinced you. Well, I don't have to convince you. JWST has opened up a new way to probe the high redshift universe. They have discovered an incredibly large number of very massive galaxies at very high redshifts. So we did two things. One, we showed that if you have a blue tilt, you can plausibly explain these things, but you will be in trouble with gravitational lensing and Hubble Space Telescope observations by using semi-analytical calculations. And then we showed that using some of the spectroscopically confirmed galaxies in the JADES program, we actually get the most stringent bound on the red tail of the power spectrum in this K. So we demonstrate that JWST can probe some really fundamental physics, the primordial power spectrum, which is a prediction from various inflationary models. And near future data set will obviously make it better. These are just 1 year data set results. I mean, JWST will run for at least 10 years, hopefully, and maybe it will lead to a discovery. Thank you. Okay, thanks.
Yes. Questions, please.
What is Z value which has been reached?
Yes, 14.
14,
This
is it?
our paper. There is again spectroscopically confirmed galaxy at reaching 14, and we are trying to.
Is there any information about gravitational waves by galaxy merger or anything?
Good. So galaxy mergers as such will not give gravitational waves, but the supermassive black holes that are hosted in them will give gravitational waves, and people are starting to look into this. But remember, JWST, there's a caveat here. This is a good question. The caveat is that JWST is observing single galaxies, right? They are not observing dual AGNs. I mean, okay, they have observed a few dual AGNs, but yeah. So this will probably boost up the supermassive black hole gravitational wave background. But yeah, things are in progress. I mean, finding dual AGNs, that means two galaxies are very close, is obviously much more difficult than finding one galaxy. But JWST has found something. So yeah, so this is something people are working on.
But those things will require. It cannot be done in LIGO or anything. It has to.
No, this is nanograv.
Nanograv.
PTA, in PTA. Yeah, this is for them. Yeah, this is for in PTA signal. So the in PTA signal may be boosted up if they're sensitive to very high redshifts. Maybe some future versions.
So do we understand well why these massive galaxies are also extremely bright, some of them? Is it something to do with the star formation?
Yes.
Does not happen continuously, but it happens in really bursts, and
yes.
then
So that
it shines really high.
Yes, so that is one of the solutions. The star formation is bursted, but you are taking a snapshot of a galaxy at one point.
Right.
So maybe at this point, for some of these galaxies, star formation was intense. So this is what is called in the astronomy community as something called a stochastic star formation.
Right.
So maybe star formation is bright and then go dim, bright, dim, maybe. And maybe we have caught them right at when it's very bright. It's obviously bright for a few mega years or something.
Okay.
You know? So maybe that is one of the astronomy solutions. The other astronomy solution is maybe the star formation efficiency is really a function of redshift, a very steep function of redshift. So that will, again, yeah, this is something in flux. We don't know what is happening. Something interesting. And maybe new physics, I don't know. Yeah. So people have proposed early dark energy, for example. Low delta.
Yes. Okay, maybe we allow Shantan to finish the question you wanted to ask. Is it later? Okay.
Okay.
So we break now. There is an announcement.
Thanks.
Ah.
Any questions? Please let me know.
Okay, so we have a tight schedule. Next session, there are 3 talks. After that,